So, we will discuss today about the internal combustion engine, rather we will continue our discussion, and we will discuss, rather I will continue our discussion on fuels, alternative fuels and octane and cetane numbers. So far I can recall that I have discussed about octane number in my last class. So, today I will discuss about cetane number. So, what is cetane number? That is very important again. We have discussed the self ignition characteristics of a fuel, and from there we have seen that the temperature above which this occurs. I mean, we have seen that for spark ignition engine we require an external agent like spark plug to ignite to initiate the combustion, but and if the compression heating of a particular fuel is always less than the self ignition temperature of that fuel, of course we require that external agent. But if it is possible to raise the temperature because of the compression heating of a fuel above the self ignition temperature, then then we can ignite fuel, we can start combustion without help of any external agents. So, we have discussed that even when that the initiation of combustion and completion of combustion require finite time, and that time is known as physical delay. So, that the ignition delay, and ignition delay has two parts, one is known as chemical delay, other is physical delay. So, in particular we have seen that for a compression ignition engine we do not have any external agent. So, we are relying on the we are relying on the fact that the compression heating will be able to raise the temperature of the fuel above the self ignition temperature, and the entire combustion will take place. So, particularly for a compression ignition engine, that is for a compression ignition engine, self ignition of a air fuel mixture is a necessary condition. So, for a compression ignition engine, for a CI engine or compression ignition engine, self ignition of air fuel mixture is a necessity. Since we do not require any external agent, we rely on the temperature and pressure of the air fuel of the air at the end of the compression, that the temperature will allow to self ignite the fuel when fuel is being injected through fuel injector. So, the self ignition characteristics or the self ignition of air fuel mixture is a necessity for a CI engine, for a compression ignition engine. So, now what is very important, that means we have seen that if I try to recall the figure that we have drawn in my last lecture, that whenever we are having compression heating we can raise the temperature above the self ignition temperature, but maybe whenever temperature goes above the self ignition temperature, ignition may initiate, but entire combustion won't be completed. So, initiation of ignition and completion of the combustion require finite time, and that time is known as ignition delay. That shorter will be the delay. We have seen this, we have seen that we can reduce the delay by increasing the compression heating temperature. That means, if we can raise the temperature of a air due to compression heating to a level, and that temperature is so high that we can reduce that ignition delay to complete the combustion. So, that means, and that also varies from fuel to fuel, because that depends upon fuel compositions, the number of carbon and hydrogen atom present in the fuel. So, the correct fuel must be chosen in a compression ignition engine with which will ignite without an external agent, rather which will self ignite at a proper time in an engine cycle. So, if we talk about the combustion of a compression ignition engine, then we have seen that there is no external agent. So, no external source like spark plug to initiate combustion. That means, the that means in a compression ignition engine, you know, the correct fuel must be chosen which will ignite without any external source at a proper time of the cycle, at a proper time of the cycle. So, correct fuel means we need to provide that. I know that the compression ratio for a compression ignition engine is this. So, knowing the compression ratio, if we can estimate that what will be the rise in temperature due to compression heating, and if we know that the fuel we are going to supply in a compression ignition engine is having this is the self ignition temperature of that particular fuel, then we can tell that without any external agent entire combustion will be completed, and for that we need to know that which fuel must be supplied. That means correct fuel must be chosen which will ignite without any external source at a proper time of the cycle, that is the fuel will self ignite, that is fuel will self ignite, very important, this is important. Now, so if we know that if we supply correct fuel and if we raise the temperature due to compression heating above the self ignition temperature, then perhaps we can say that without any external agent entire combustion will be completed. So, for that we require knowledge and control of ignition delay. This is ID, ignition delay time of fuel, right. So, if we know that fuel will self ignite because of the compression heating, so correct fuel must be chosen, this is important. Not only that, we require knowledge and control of the ignition delay of the fuel. So, how we can reduce the ignition delay and what will be the ignition delay for particular type of fuel, we need to know. So, the property that quantifies this is called called Seton number. So, the property that quantifies this is called Seton number of fuel. So, this is very important, that means since no external agent is there for the initiation of combustion in a compression ignition engine, we should select proper fuel. Not only that, we should have an understanding and control about we should have a knowledge and control about the ignition delay of that particular fuel. So, the property that quantifies that describes this is known as the Seton number of the fuel. So, just like an octane number, again Seton number is a numerical value and the scale numerical scale, and you know the Seton number are established for any particular fuel by comparing the test you know that fuel to two reference fuel. So, just like octane number, if I like to know the Seton number of any particular fuel, then we have to take that fuel for you know for a test in an engine at certain specific condition, and we need to know the Seton number to two reference fuels. So, that two reference fuels are you know one is known as N-Seton, one is N-Seton, whose cetane number is 100, another is heptamethyl-nonane HMN, heptamethyl-nonane whose cetane number is 15. So, knowing the value of cetane number of two standard fuels, one is N-cetane whose cetane number is 100, another is heptamethyl-nonane whose cetane number is 15, we can calculate cetane number of any given fuel on doing a test in an engine at certain specific condition with reference to this particular fuel. So, there is a formula. So, if we like to calculate cetane number of any fuel is equal to percent of N-cetane plus 0.15 into percent of heptamethyl-nonane. So, knowing these two standard cetane number of two standard fuel, we can calculate cetane number using this. Of course, we need to do test in a certain engine at certain condition. Okay, with this, now we next move to fuel for the engine. So, fuel for internal combustion engine, very important. So, major classification is number 1 solid fuel, number 2 gaseous fuel, number 3 liquid fuel. So, we can have internal combustion engine can be operated on different kinds of fuel including solid, gaseous and liquid. Now, the use of solid fuel is creates rather presents problem. What kind of problems we are having if we use solid fuel? One is it is complicated injection system, because if we use solid fuel we have to inject fuel in a engine. So, it is a complicated injection system. Not only that, difficulties associated with the solid residue or ash. So, if we use solid fuel, one problem is the injection system, and another problem is after combustion we will have solid residue or ash. So, there I mean removal of that and from the engine is again problematic. So, solid fuel cannot be used in internal combustion engine, although for external combustion engine we have seen that we can use solid fuel like coal. So, another fuel is gaseous fuel, is very important. Gaseous fuel create problem concerned with storage and handling. So, solid fuel is having problem with injection system and removal of solid residue or ash. Gaseous fuel is having problem that handling and storage, because you require bulk storage tank to store that gaseous fuel. Also the handling of large volume. So, volume will be large. On the other hand, the seriously this handling rather of gaseous fuel require bulk and large storage tank, which seriously restricts the use of such fuel in mobile equipments. We cannot use, because it requires a huge and large bulk storage tank. But if we use gaseous fuel, such fuels reduce many of the problems of starting and distribution that are encountered with liquid fuel. So, as compared to liquid fuel, if we compare, as compared to liquid fuel, the use of gaseous fuel to some extent advantageous, in a sense that starting and distribution of the fuel. Some gaseous fuel cannot be liquid, I mean it is not, because liquid fuel is having inertia, so it is not easy to distribute and transport one point from one point to other point. On the other hand, gaseous fuel can be easily distributed. So this is one of the advantageous features of using gaseous fuel. Some gaseous fuel can be liquefied at high pressure, but it is costly. So we do not use gaseous fuel, we require. So most of the engine IC engine therefore utilizes the liquid fuel which are derivative of petroleum. So we have seen that solid fuel is having problem, this is having problem of injection system, difficulties associated with injection system and removal of solid residue or ash. So this is very important. Gaseous fuel requires large storage tank which seriously restricts the use of gaseous fuel in mobile equipments, requires large storage tank, but it is having advantageous feature. Advantages, I mean is very important, reduce the problem of distribution that are encountered with liquid fuel. So this is the advantage of using gaseous fuel. So most of the internal combustion engine use liquid fuel. Most of the internal liquid fuel which are derivative of petroleum. In some countries where natural petroleum is scarce, fuel having very similar compositions and characteristics are being produced by hydrogenation of coal. There are countries where natural petroleum is scarce, they use very similar composition and characteristics of fuel. They use fuel having similar compositions and characteristics, and those are produced by hydrogenation of coal. So most of the internal combustion engine use liquid fuel which are derivative of petrol, but where natural petroleum is scarce, their fuel of similar compositions characteristics are being used or produced by hydrogenation of the coal. As I said that liquid fuel are basically a petroleum product. So normally I will just give you a basic idea how we get product several petroleum product from crude oil. So normally I can write this is crude petroleum that is obtained from crude oils, and the crude petroleum which is classified on the basis of residue left after distillation, classified on the basis of residue left after distillation. Then this crude petroleum is taken into oil refinery. This is taken oil refinery. So this will give you how we can extract petroleum product, derivative of petroleum from crude oil or crude petroleum, since this crude petroleum product are mostly used as a fuel for the internal combustion engine. So, this is oil refinery. Here distillation occurs at atmospheric pressure, and this oil refinery consisting several towers of refinery, consisting several towers. Then we get which is known as straight ram product. We get a straight ram product, that is product after distillation. Which is known as straight ram product. So, product after distillation is known as straight ram product, and the straight ram product, from there we can obtain the final derivative, and for that we may require certain chemical processes or chemical treatment. So, subjected to further chemical treatment which is required, that those are basically known as polymerization or cracking. So, subjected to further chemical treatment, we can get the final petroleum derivative which is required for any SI and CI engines. So, depending upon the, as I said you a few minutes back, that we need proper fuel. So, proper fuel means whose self ignition temperature I know. So, and I know the ignition delay, because ignition delay has two parts, as I said last class, physical delay and chemical delay. Chemical delay is highly associated with the chemical composition of the fuel. So, depending upon the structure of carbon and hydrogen atoms and number of hydrogen and carbon atom, we can tell what will be the ignition delay, chemical delay, and what will be the self ignition temperature. So, to obtain that a special or particular fuel for any particular engine, we need to do a further chemical treatment of the straight ram product, and those treatments are polymerization and cracking. So, this is essentially the flow path process from which we can obtain the final petroleum product from the crude petroleum. As I said you that this crude petroleum comes from the raw petroleum comes from the oils. So, whenever we are getting crude petroleum, it consists many hydrocarbon of different molecular weight. So, it also contains sulfur, nitrogen also. So, crude petroleum contains many hydrocarbons of different molecular weight, also contains sulfur, nitrogen. So, basically crude falls into three classes depending upon classified on the basis of residue left after distillation crude petroleum. So, this crude petroleum can be classified, basically fall into three classes depending upon whether the residue left after distillation in many is mainly. So, depending upon the classified, it is basically three. One is known as normal paraffin or wax or something combination of these two, sometimes combination of these two, asphalt or asphalt. So, depending upon the residue left, we can classify into three categories: normal paraffin, wax, and or combination of two. And the corresponding crudes are known as either paraffin based or wax based or the combination of these two. Then we take that crude oil into oil refinery where distillation process takes place in atmospheric pressure, and during this process distillates are separated into various factors according to the volatility, right, because then we take crude oil into the oil refinery and there we do distillation at normal, at atmospheric pressure, and there this the distillates is separated into various factors according to volatility, and then finally you will get straight run product. The distillates are called straight run product, and then again we need to go for various chemical treatments like polymerization cracking to obtain the desired fuel which is required for the operation of either SI or CI engines. Fine. So, normally these fuels are basically the above 5 are hydrocarbon family. One is the hydrocarbon family, as I said you, the hydrocarbon family. One is paraffin, paraffin whose formula is CnH2n, CnH2n plus 2. Number 2 is olefin, CnH2n. Number 3 is diolefin, CnH2n minus 2. Number 4 is naphthene, again CnH2n, and number 5 is aromatic, CnH2n minus 6. So, these 5 are the above 5 are hydrocarbon family. So, now I am writing two important. Normally this paraffin are suited for CI engine and aromatic are suited for SI engine. A thumb rule is that if number of carbon atom increases, then molecular weight increases, then molecular weight increases, consequently boiling point increases. Right. Second is, if hydrogen is to carbon, the ratio of hydrogen is to carbon ratio increases. So, H is to C ratio increases, then calorific value of fuel increases. Calorific value of fuel increases. So, that means if the number of carbon atom increases, the molecular weight will increase, boiling point will increase. On the other hand, if hydrogen is to carbon ratio increases, then calorific value of the fuel will increase. As I said you that the crude petroleum which consists of large number of hydrocarbon compounds differing, as I said you that crude petroleum consists of a mixture of hydrocarbon differing widely in molecular structure. It is desirable to arrange the hydrocarbon compounds into families based on the hydrogen carbon arrangement within the molecule, right. So, crude petroleum which consists of a mixture of large number of hydrocarbon of different molecular weight, of different molecular structure of it is desirable to arrange these hydrocarbon compounds into families. Crude petroleum consists of a large number of hydrocarbons differing widely in molecular structure. So, it is desirable to arrange the hydrocarbon compounds into families based on the hydrogen and carbon atom arrangement within the molecule. So, if we classify, so the classification based on the hydrogen and carbon atom arrangement, arrangement. So, as I said you that number 1 is paraffin whose formula is HCnH 2n plus 2. So, if I take for normal paraffin, the carbon atoms are connected together as a chain with hydrogen atom filling the empty valencies. So, if I take normal paraffin, so the chemical formula this type is CnH2n minus 2. The normal paraffin carbon atoms are connected together with as a chain. In a normal paraffin carbon atoms are connected together as a normal chain with hydrogen atom filling the empty valencies. That means what we can see, the valence of each carbon atoms atom is fully utilized. In combining by a single bond with other carbon atoms and with hydrogen atoms. The straight chain paraffins are saturated compounds and characteristically very stable. So, this is very saturated compound. So, this is saturated compound, no empty valences, no double bond and characteristically very stable. Very stable, right. So, this is paraffin, and we will discuss that these paraffins we will discuss in later. Similarly, if we take olefin, number 2 olefin, that is CnH2n. So, say C4H8. So, we will have the structure is like this. These are chain compound similar to paraffin, but unsaturated and unstable because they contain one double bond. So, similar to normal paraffin, they are chain compound one, but unsaturated and unstable because they are having one double bond. So, butane is a typical example. So, this is butane, that is butane, a typical example. 3 is very important. So, this is unsaturated and unstable. 3 is diolefin. Say CnH2n minus 2. So, diolefin CnH2n minus 2 and say butadiene C4H6 butadiene, and if I try to write the so this is the chemical structure. So, this is essentially olefin with 2 double bonds, and they are unsaturated and rather unstable, tending to form gun deposit during storage, and their general formula. So, this is diolefin essentially. So, these are diolefin are essentially olefin with 2 double bonds. Number 2 is they are unstable and unsaturated, and tending to form Gann deposit during storage. They are so unstable and unsaturated, they tends to form Gann deposit during storage. So, this is a this is diolefin. Similarly, 4 is naphthene, whose formula is CnH2n, that is C5H10, C say C5H10. So, if I write if I draw the structure, so this is the structure. These are characterized by a ring structure as shown in as follow. So, these are characterized by a ring structure. They are saturated and stable. Since they do not have double bond, they are saturated and stable. And finally, we are having aromatic, that is CnH2n minus 6, say C6H6 benzene ring. So, we know their structure. So, basically they are ring structure, compound, ring structure compound, based on benzene ring, while double bond indicate unsaturations, indicates unsaturation, although while double bond indicates unsaturation, a peculiar structure, a peculiar nature of these bonds double bonds cause this family to be more stable than the other unsaturated family. A peculiar nature of this bond makes this family to be more stable than the other unsaturated family. Right, it is very important. Although they are having double bond, that indicates unsaturation, but the peculiar nature of this structure makes this family to be more stable than the other unsaturated family. Okay. So, out of these discussions, I would like to make a few more general characteristics, a few of the general characteristics exhibited by this family due to their molecular structure and due to their molecular structure, due to their molecular structure are summarized below. So, very important. So, we have discussed about the different families of hydrocarbon: normal paraffin, olefin, diolefin, naphthalene, and aromatic. So, a few of the from the discussion we have done, we can make a few more general characteristics exhibited by this family because of their due to their molecular structure. Number 1, the anti-knock. We will discuss what is anti-knock. The anti-knock quality of a fuel when used in SI engine appears to be poorest in the normal paraffin. The anti-knock quality, we will discuss the combustion and then we will come to know the why what is anti-knock quality of a fuel. So, the anti-knock quality of fuel when used in SI engine appears to be poorest in the normal paraffin, in the normal paraffin. The aromatic offers the best resistance to detonation in SI engine. The aromatic offers best resistance to detonation in the engine, to detonation in SI engine. So, very important. The anti-knock quality of the fuel, if we use normal paraffin as a fuel in SI engine, the anti-knock quality appears to be poorest. So, the aromatic is the best solution for this and because of this molecular structure. Fine. For CI engine, for CI engines, the normal paraffin are the better fuel and aromatics are the least desirable. The normal paraffins are the better fuel and aromatics are least desirable. 3. What is 3? In general, as the number of atoms in the molecular structure increases, as the number of atoms in the molecular structure increases, the boiling point temperature rise, then the fuel with fewer atom in the molecular tend to be more volatile. Then boiling temperature rises, thus the fuel with fewer atom in the molecule, the fuel tends to be more volatile. And finally, 4, very important, that as the proportion of hydrogen atom to carbon atom increases, heating value increases. This is because hydrogen has a higher heating value than the carbon. So, paraffin and paraffin tend to have greater heating value than the aromatic. So, if as the proportion of hydrogen atom to carbon atom in the molecule increases, the heating value of the fuel increases. This is because hydrogen atom, the hydrogen molecule increases. This is because hydrogen has higher heating value than carbon. So, paraffin thus tends to have paraffins thus tend to have greater heating value than aromatics. So, we have discussed about this molecular structure of the different hydrocarbon, and we have discussed that whenever we are getting straight ram product and further after treatment with either polymerization cracking, we may obtain different hydrocarbon of different structure. So, since crude petroleum consists of family of hydrocarbon, that is a mixture of hydrocarbon of large number of hydrocarbon compounds differing widely in molecular structure, it is desirable to arrange this hydrocarbon into families based on their hydrogen and carbon atom arrangement within the molecule. So, and based on that arrangement we have defined paraffin, olefin, diolefin, naphthalene, aromatic, and we have seen that paraffin is stretched. We have discussed that paraffin is basically chain compound and is very stable and saturated compound, because we did not see any double bond over there. Olefin is chain compound, but because of the presence of double bond it is unstable. Diolefin is essentially olefins of two double bonds, but they are unstable and tend to form gun deposit even during storage. Although naphthalene is not as chain, it is not chain structure, rather it is ring structure, and they are saturated and stable. Aromatic, although we are having double bonds, they are essentially ring structure based on benzene ring. Although we are having there are double bonds, but because of the peculiar nature of the peculiar structure of these double bond, these family are more stable than the other unsaturated family. From this we have obtained a few general characteristics. Those are that if I use paraffin in a SI engine, since the antenna quality of the paraffin appears to be poorest, so while aromatic offers best resistance to detonation in the SI engine. For CI engine, normal paraffins are better fuel than, and aromatics are least desirable, and because aromatics are very stable, it is not, we can't decompose it, because in CI engine we need to have self ignition characteristics, so it will easily decompose. And I have discussed beginning that if the number of carbon atom increases, the molecular number of atoms in the molecular structure increases, boiling point temperature will rise. So, the fuel with fewer hydrogen atom in the molecular tend to be more volatile, and as the proportion of hydrogen is to carbon atom increases, heating value will increase, because hydrogen has higher heating value than carbon, and paraffins thus tend to have greater heating value than the aromatics. So, with this I stop my discussion today, and we will continue our discussion. We will discuss about the alternative fuels like methanol, ethanol and natural gas in the next class, and also we will discuss about the antenna quality, of course, when we will discuss about the combustion of CI and SI engines. So, with this I stop my discussion today, and I will continue my discussion in the next class. Thank you.